Welcome everyone. The lecture today is going to be about set theory, and this is going to be the kind of the introduction to set theory. So this is very important, whether you're a mathematician or you're a future mathematician, or whether you're an engineer or a future engineer, or somebody that's going to be in some sort of professional development. Set theory is kind of like the foundation for the language of mathematics. It allows us to encapsulate information that may contain a lot of complex kind of objects, and it basically puts it in kind of a bag that we just essentially hand off the bag instead of trying to describe over and over the elements that we are handing to the audience that we're talking to effectively. So I would like to point out there are a lot of spoken languages on the world. Some of them share some common foundations, some common origins, and so some of the words will have some overlap, like maybe between Spanish and English. Other languages, there may not be a whole lot of overlap. So it is very possible that two people, two professionals, two mathematicians, two engineers, two developers, whatever, they may not share a single spoken word in common. However, through the use of mathematical expressions that are usually kind of symbolic in nature, they will be able to communicate quite well without being able to speak to each other in their spoken languages at all. In fact, two mathematicians or two engineers will be able to communicate a significant amount of information without actually sharing a single word, just basically writing out descriptions. It's very possible sometimes that whenever we write mathematical expressions, very concise mathematical expressions could be expanded out into extremely wordy paragraphs effectively. Now, the idea is that whenever we use sentences to describe mathematical objects or engineering objects, you tend to either lose precision, or if you have precision, it tends to be very wordy. What happens is mathematics is a language that's very concise and very dense with information, and it's pretty uniform through people that are familiar with it. It doesn't matter what your spoken language is, you'll be able to communicate with another mathematician quite well. But before we learn that formal mathematical language, we have to kind of get the very basic part of it called set theory under our belt. So this lecture is going to be an introduction to set theory. And it's probably the starting point into your path as an engineer or a mathematician. So let me transition to my notebook and let's get started. All right, so there's three ways to represent a set. I guess, well, actually, before we get to that, let's have a brief conversation about what a set may actually be. So let me just get my pen set up here. Sorry about that. Let's suppose that we have a whole lot of objects. I'm just going to draw circles to represent objects. And let's suppose that I have a whole bunch of them. We just have a whole bunch of objects. Now, this is kind of maybe just a handful, but let's suppose that these objects could be very complex. Perhaps these objects are cars. Perhaps these objects are people. Perhaps these objects are just notions in our mind, or maybe they're colors, something abstract that you can't touch. Maybe this one is blue. Maybe this was the object green. Maybe this object is the color yellow. Maybe this object is a Ford truck. Maybe this object is a Jeep Rubicon. Maybe this one is a Tesla truck. Who knows, right? They could be anything. Now, whenever two people are communicating mathematically, they need to maybe share the information about these objects. So what may happen is maybe this person will describe this object, and then maybe this person will describe this object, and then this object, and this object. And every time they make a reference to these objects, maybe they would say, oh, well, consider those objects red, green, blue, yellow, whatever, and then you go through. That would be very cumbersome if you had to keep repeating those objects over and over. Or if you had some way of saying, let these objects be all the colors found in the rainbow, or the colors that are most commonly found in some sort of decoration in a home. Who knows? Well, every time they made a reference to it, maybe they'd had to say, well, assume that these are the colors of the rainbow, or maybe consider the colors of the rainbow. That would eventually get kind of wordy, and you had to keep saying it over and over. What may actually be the case that would be a lot better is that the mathematician may put all of these objects inside of a container that we call a set. And then maybe that person will just label this as set A. So initially what this person will do is whenever they're trying to communicate to this person the set of objects that they're discussing, they will define it exactly one time, and then they'll say from now on, all those objects will be referred to as the set of objects that I'm going to call A. And so then the mathematician will always refer to set A, and then there will be an understanding that this other person knows that that was those objects that was previously defined. So in computer science, we often refer to this as kind of encapsulation. If you remember that from your C++ days, let's maybe have some discussion here about computer science that's almost closely related to set theory. If you're okay with this, this may be slightly abusive and how overly simplistic it is, but I think it actually kind of drives things home. If you remember maybe in your C++ class or your C class or even Python, whatever, all languages kind of have this way of encapsulating data for the most part. Let's suppose that we have some fake function. Okay, we have some fake function, and this function is going to have a set of parameters where maybe we have int A, int B, maybe we have string C, and then we have maybe another int, I don't know, D, and then we close it off down here. And then we have all these places in our code to where we're calling this function, right? And every time we call this function, we had to pass in int A, int B, string C, and then int D. And then all of a sudden, we have maybe this place called, maybe we have like over 5 places where we're calling this function, right? We have 5 different places in our code where we are calling this function. And then all of a sudden, we decide, you know what, we need to update fake function to now have, maybe we're going to add a new thing called int E. Well, kind of the unfortunate thing is, excuse me, one of the unfortunate things is that all these 5 places where we're calling that fake function, we had to go back and then update them all to then say int E. We also have to add that parameter to all 5 of those places that we're calling fake function. And then tomorrow when we add int F, we had to go back through and we had to add that to all the places that we call it. So whenever the parameters start growing as a big list for a function, what may be better, if you guys can recall, is that we create what's maybe called a struct, where then we define a struct and we just essentially put all of these variables inside the struct. We say int A, int B, int C. And then instead of having fake function have these individual parameters, we say fake function will just accept a struct. It'll just accept that struct. And this is kind of pseudocode. I'm not going to pass around the ampersands, the arrows, the dots, and all these things. You just guys get the idea. So basically what we're going to do is we're going to kind of encapsulate every one of these parameters into like kind of a little bag. And then instead of like handing the individual objects over each individual time, we're going to put it into a struct or a bag. If we're talking maybe more loosely speaking outside of computer science, we're just going to put all those parameters inside of a bag. And then what we're going to do is we're just going to hand that bag to the function, and the function kind of unpacks it and then uses as needed. Now, what does that benefit us? At that point, anytime that we need to add a variable, we don't have to go through and add it to each one of these new places. We just add it to the struct, and then wherever we're adding the values to the struct, we just add it there. And then all throughout the code, we don't have to be messing around with parameters and adding parameters all over the place. It makes the code more nice and neat. It makes it more compact. We get to use a word like encapsulation to like show off to our friends all the wonderful words that we know. It just works out very well. Well, what encapsulation to a computer scientist is what we refer to set theory effectively in mathematics. Now that's almost so overly simple that it's almost abusive, but that's kind of the idea that you should, as a new student to set theory, that's what you should be thinking about whenever I say the word set theory. Now there's another example if you want to talk about it. Keep in mind, whenever you are like, suppose you have a bunch of files and you need to send them to someone else. Maybe there's like, maybe you are this person and then maybe your friend is over here. Maybe we'll give these people's arms so that way they look like humans. Let's suppose that you have file A dot text, then you have file B dot text, and then you keep going, and there's effectively 100 files here, and you need to email these files to this person over here so that way they have these files, right? Now, wouldn't that be terrible if you had to go to a folder and you had to like select all 100 files, and then you click send, and then all of a sudden your computer does what? The email server says, oh, well, there's a cap on how many files that you can transmit. Now, just imagine the person on the receiving end here who just got an email with 100 file attachments to it, and they had to sit there and click and download each one of those individually, then open them up. How terrible would that be? I'd be kind of mad if my friend sent me 100 files and say, here, look over these. Well, what we may do is we may just do the old select all and then put them into a zip folder and then email the zip folder, and then whenever that person gets that zip file, they decompress it to get the individual files. Again, that's effectively what a set does in mathematics. It essentially takes a bunch of objects that may be difficult to describe individually, or there may be a bunch of them, and we just kind of encapsulate them into one big kind of container, and then from then on we describe it once, we put the objects into that container, and then from then on out, whether we're talking about the publication that we're publishing or we're talking about the manual that we're writing for the documentation, whatever the case is, we just refer to that name. Like we refer to this as set A. We'd say let all the elements of set A, we do this with them, do that with them, whatever. We've essentially now condensed the whole thing into just a letter name, set A. That's effectively what we got. Okay, now there's three ways to represent a set. There's three ways to represent sets. Okay, there's three ways to represent sets. The first way is sentence form. Now, what I want you guys to know is this is the worst way to do it. This is absolutely the one way that we want to avoid it as mathematicians, professional engineers, professional developers, whatever the case may be. This is what we want to avoid. And the reason is because this tends to be either wordy or very imprecise. So let me just say this out loud. How many guys, just think to yourself, how many of you guys ever been around young children? They kind of have their own literal way of taking things we say very literally, right? I mean, after all, they're very young. They haven't got a lot of life experiences. If they weren't children, we'd refer to them as kind of being silly, maybe something worse. But anyway, imagine you're at a birthday party and you ask the children there, pick a number between 1 and... How does a child know whenever they're going to be the first in line to pin the tail on the horse? We had to form a line, right? Somebody has to be first, somebody has to be last. No, every kid there wants to be first. So what does the adult in the room say? I'm going to pick a number, and I want you guys to pick a number, and whoever gets closest to my number, they get to go first. You know that little trick, right? Okay, so what happens is the first kid comes up, and they say the number 3. Okay, that's great. Then the next kid comes up and says the number 20. And you're like, kid, why did you pick the number 20? Because typically when we play this game, we all say, I'm thinking of a number between 1 and 10. And then you got little Johnny over here who says 20. And you're like, where did that come from? Well, actually, whenever you said that, you said pick a number. You didn't actually specify the number. Okay, now you got to back up and you got to tell all the kids, pick a number between 1 and 10. Now you've made it a little bit more clear. Okay, well then one of the kids raises his hand and says, hey, can I pick the number 1 or can I pick the number 10? And you're like, what is this kid? But then you think about what you said. You said pick a number between. Does that imply that the endpoints are actually included? Could you pick the number 1? Or did you mean that it started out with number 2? Or did you actually mean that number 1 is a number that you could pick? Okay, then you back up and you say, okay guys, pick a number between 1 and 10 and that allows for the numbers 1 and 10 inclusively. Okay, then all of a sudden you got Sally who says, okay, I picked pi. And you're like, well, pi, a kid at a birthday party just said pi, the 3.141592 on to infinity. Well, yeah, technically by what you said, that's quite in bounds, right? Because you said pick a number between 1 and 10, inclusive 1 and 10. Well, technically pi is in that range, so then you had to back up and you had to say, okay kids, pick a number between 1 and 10, including 1 and 10, and it has to be a whole number. At that point, you've pretty much defined it, but just think of how many words that you had to say to a group of kids at a birthday party just to make precise known what you meant, right? That's what tends to happen in publications when we use sentence form. If we stray away from mathematical representations, we invite the problem of being imprecise, or if we are precise, we tend to be so wordy that we lose our audience, right? So, what's the benefit of this? Is it is easy, and this is something that everybody could digest. The problem is it tends to be not precise, and it tends to be wordy, right? Wordy. New word of the day, wordy. So it is easy. It tends not to be precise, tend to be wordy, but sometimes that's what we have to do. There are some complex objects to where we may not have had a lot of definitions associated with it, or it may not be a super well-formed area of engineering or mathematics, or maybe our audience is not familiar with the representation. Sometimes we have to go to sentence form, and that is just what we have to do. But we want to avoid it. So our next best bet is roster form. Roster form. This is just like a classroom roster. It is basically an explicit list of elements. It is basically an explicit list of the elements in the set, just like a roster. How do I know if somebody's in a class or not? I look at the roster. If Sam is on the roster, Sam is an element of my set. If Sam is not on my roster, Sam is not an element of my set. Typically, the way we might do this is it looks like this. We would say, let set A be the set of elements 1, 2, 3, 5, and 11. Notice how I have these two curly braces. These curly braces are effectively how I represent a set using roster form. We say, is 1 in the set? Yes, it is. I look in the roster, there it is. Is the number 5 in the set? Yes. Is the number 7? No. This is the easiest thing probably that we could hope for. Now the problem is this only works out well for sets that are relatively small, right? I mean, imagine if I have a roster form of a set containing 1 million elements, or a set that has an infinite number of elements in it. That's possible. We'll learn about that here in a minute. Do you see how that would be problematic? At that point, we had to almost have like a computer help us where it'll iterate through the elements to determine whether something's in there or not, right? That could be a little bit of a problem. Well, it turns out that we do kind of have some shortcuts. So let's suppose I want to represent all the whole numbers from 1 to maybe 1,000. I could do something like this. I could say 1, 2, 3, 999, 1,000. Now, for those of you guys that are the English majors, you guys know that as ellipse. So basically, whenever we have ellipses, whenever we have the numbers 1, 2, 3, we essentially established a pattern. That ... means the pattern continues. And then we have the pattern terminate nice and rounded out with 999 and then 1,000. So we ask, is the number 500 in this set? I don't actually have it written, but it's clear that that is part of the pattern. 1, 2, 3, 4, and 500 would certainly be in there. So would 700. However, the number -50 would not be in there. It's obvious that the number 22,000 is not in there. So we can actually maybe condense this. Now, it is possible that sometimes an infinite set can be represented this way, where we have 1, 2, 3, ... Now, in this case, this is an infinite set, to where the set goes 1, 2, 3. It's clear that the number 5 would be in there. It's clear that the number 7 would be in there. It's clear that the number 528 would be in there. It's also clear that 1,002,123 would be in there as well. What would not be in there would be like 7.25, right? So we can have infinite sets that way. Now, what's the benefit of this? Roster form works out well. It's good for small sets. It's good for sets that form nice patterns. Okay, it's good for small sets, and it's good for sets that form nice patterns. Okay, So what about these instances where we don't have nice patterns? Well, at some point, there are some sets to where we just have awkwardness and we just have to maybe explicitly list them or we have to do something else. But it also turns out that some sets have elements that can be constructed in a certain way. At that point, we have what's referred to as set builder form. Now, this is one of the reasons the Python programming language got so much traction, is because sometimes the Python language, for those of you guys who are familiar, you would say for X in the range whatever. It's basically, you can do list comprehensions. It's one of the most powerful things about the Python language is list comprehensions. And the reason for that is that a lot of things in Python kind of follows a set builder form, and lambda expressions in languages like Java and C++, a little bit harder to see. In Python, you end up with these kind of things where it's almost like you're kind of building a set in a way, or building a list, and it's just kind of nice and neat. So the best way to describe set builder form, for those of you guys that are like me and you absolutely love food, sometimes you go online and you look up a recipe, right? In this recipe, after you hit close for all these JavaScript ads that keep popping up and annoying you, you eventually arrive at something where you have the list of ingredients and then you have the directions for how to use those ingredients. And this is kind of the best way of thinking about set builder form. The way set builder form is, it essentially declares a set of ingredients. And then there will be a section where it tells you how to use those ingredients. So let me give you an example. In roster form, let me show you this. Let's let set E be the set of even numbers. 0, 2, 4, 6, 8, ... And they go on forever, right? The set of positive even numbers. 0, 2, 4, 6, 8, and then there you got it. All right, so how do we represent this in set builder form? Well, here's what I'm going to tell you. Sometimes set builder form relies on other sets to construct new sets, and I'll show you how this works. Set E can be represented this way. Set E is the set of numbers 2k such that k is in the set 0, 1, 2, 3, ... Now, what I want you guys to realize is that k, this is a set 0, 1, 2, 3, all the way to infinity. What we're going to do is we're going to refer to that as the ingredients. That's the ingredients. And this part right here is the directions. So let me show you this. E in roster form looks like this. 0, 2, 4, 6, 8, ... and we'll cut it off there. Now, what I want you guys to look at what k is iterating over. K is iterating over the number 0, 1, 2, 3. But what I want you guys to look is this is the directions on how to use it. So what's the first k? It's 0. So what do I do with that 0? I multiply it by 2. So this is 2 times 0. This is 2 times 1. This is 2 times 2. This is 2 times 3. Now with that said, take a look at this. What do you notice right here? This value, this value, this value, this value, they are incrementing up through the values that you defined right here as the ingredients. Notice that this 2 is being multiplied by each one of those values you're incrementing over. I don't know what's happening here. I've got some sort of highlighting happening. This autocomplete, sorry about that. So you've effectively got this value right here, 2, being multiplied by all the values of k. So this is the directions. Notice that the 2 stays for each one of these, and that the k is iterating over the set 0, 1, 2, 3. So effectively, we see that the set of even numbers can be written in set builder notation, where the ingredients is another set k that iterates over 0, 1, 2, 3, ... And the directions say multiply each one of those by 2. And then all of a sudden, you construct the set of even numbers, and you can represent it in roster form. So, as far as mathematical maturity, sentence form implies a very low amount of mathematical maturity. But sometimes we just have to do that. Sometimes that's just where we're stuck at. Roster form is kind of what we hope for if it's a small or a set that forms a nice neat pattern where we can do dot, dot, dot. We can establish a pattern. Dot, dot, dot means the pattern continues. And then set builder form, this is kind of like when we brag to our friends and say, you know what, I truly have a pretty good amount of mathematical maturity because I know how to construct sets using other sets. And that happens, right? And if you think about what engineering is, what is engineering? Isn't engineering where we take tools and then we make better tools? We take what we have, use our tools, and improve it. Now we have new tools. We take our old tools, we use our new tools, we improve. And then all of a sudden we have went from horse-drawn carriages to cars that were kind of like, kind of a strange kind of concoction, to now we have very modular cars to where, like, if something breaks, we could take that one part off, put it back on there. We have the tools to take it off, the wrench, the impact drivers, whatever we got, and we have a very sophisticated system of doing things. Our computers, they used to be relays. Now they're transistors. Now we're using chemical processes to make transistors that are only a few gold atoms apart. Right? Billions of transistors on something the size of your thumbnail. All right, so that's basically set theory. Set builder notation is how we take other sets and construct new ones. Roster form, we just have an explicit list. Sentence form, we just basically have to describe it. Each one of these has a pro and a con, which is just up to us to pick which one's best. It also depends whenever we're presenting this to a crowd. It depends on their mathematical maturity. It would do me no good to do set builder form if nobody understood it. In that case, I may have to do sentence form. And so any loss of clarity I might have may not be a big deal if people are not like intended to understand all of it. If it's being a very precise thing, we might use set builder form so other engineers could know exactly precisely what we mean and how it's constructed based on how the sets we're using were precisely constructed, right? Okay, so with that said, that's the 3 ways that we represent sets. What are they? They were sentence form, they were roster form, and set builder form. Okay. Now, another part of sets, let's talk about the properties of a set. Properties of a set. There's really only 2 that I expect you to really know. Now, we can go quite deep into this, and we will at some point, but the properties of a set, there's 2 of them. Number 1, there is no order inside of a set. What I want you guys to imagine is that, so here at my house, we go through periods of extreme clutter, and then we decide to throw everything we own in the garbage and start over, and then we got a clean house. So during those intermediate times, sometimes we come home, and whatever's in our pocket, we come home, and then on our shelf somewhere, we have a bowl. And then whatever we have, whether it be the pennies or it be the Walmart receipt or who knows what, a piece of chewing gum, all of that just goes right inside the bowl. We walk into the door, we grab our pocket, we put it in the bowl, and that's where it sits. Now, the idea is that maybe this bowl has some sort of, it has things that's inside of it, right? Now, imagine that I put my hand over that bowl and I shook up everything inside there. That would reorganize the contents of the bowl. But the idea of the bowl is it just holds things. I don't necessarily expect the chewing gum to always be on the top. I don't always expect the Walmart receipt to be on the bottom. I don't always expect to see my spare change in the middle somewhere. When I shake it up, it's all reorganized. But it really didn't matter because all of that's just in there to be held until I had to look through it and find what I'm looking for. If I need to return something at Walmart, I'll know it's in the bowl. I'll dig through the bowl and then I'll get that Walmart receipt out. If I'm going to some place maybe to wash the car and I need to do the vacuum maybe, or I need to go to a Coke machine, maybe I'll grab a few quarters out of there and I'll take the quarters with me. So it does not really matter the organization of the bowl. It's just the fact that it's holding the things that I know what's in there. So that's one of the properties of a set. There is no order. You can rearrange a set any way you want to. So let's suppose that set A is the set 1, 8, 2, and 5. Now that looks awkward because a lot of times we want our everything to be kind of nice and neat. By the way, I've got an Apple update here to where it's like trying to this is kind of new. It's highlighting things when it sees as a math expression and it's trying to like figure things out for me. I'll figure out a way to turn that off by the next video. But for right now, let's just deal with it. Apple's trying to figure out what it is I'm trying to do with these little squiggle things. Now let's suppose now that I decide, I don't really like the way that looks because it feels awkward to put 8 in front of 2 and then 5. So what I could do is I could just simply rewrite A as 1, 2, 5, and 8. Now notice that's a little bit easier for me as a human to digest. It kind of helps me keep a track. It kind of maybe helps me sort out which numbers are in there or not. But in fact, these two things are equivalent because a set doesn't have an order. Now, if you guys go up here and think about roster form, notice how I wrote these things in an order then did ... There are some times when we represent a set with an order just because it helps us as humans keep track of what's in there or allows us to use the ... notation for big sets. But the idea is that the order doesn't matter. In that case, we're just using an order to help us out. But we could shake that bowl up and rearrange it any way we want to without causing any problems. That's the first property. The second property is there are no duplicates. Now this can actually go kind of deep. So there's no duplicates. This needs to be described. This needs to be explained. So we have set A, and we said that that had the number 1, 2, 5, and 8 inside of it. And I got my closing braces. Maybe I need to make it a little better. We got our closing braces. Now what happens if I just go ahead and I decide, you know what, I'm going to put another 2 inside of here. I'm going to put another 2 inside there. After I add that number 2, guess what my set looks like? You may be inclined to think, well, this will be 1, 2, 2, 5, and 8. But that's not the case. That's not what would be the reality. We'd essentially have this same thing. Why? Because when you add something that's already in a set, it just gets absorbed, and so it's basically just the number 2 stays in there. So if it's already got a 2 in there and I add a 2 to it, it just has 1 2 in there. That doesn't get 2 2s, it just has 1 2. So there are no duplicates. Now there are times where we need to be specific about what we're calling a duplicate. So let's imagine that we have 2 children. Let's suppose that we have like a set of children in a set, right? I mean, why not just make children the object, right? We have children inside of a set. We're going to say maybe, let's let set K be the set. Maybe we have little Sam, we have little Bob, and we have little, I don't know, John. How about that? Pick the most basic names we could think of here. Sam, Bob, and John. Now let's suppose that Sam, she has an identical twin. And let's just take this to real extremes. There is absolutely not a single physical difference between Sam and the identical twin, except that it's a separate person, right? And we'll call this other person, I don't know, Katie, right? So we'll put this person in there. Now, in that particular case, adding Katie to the set may be allowed. Why? Because when we consider humans, even though we may have 2 that look identical, they are 2 distinct humans, right? Maybe we could think of a set of pennies. Every penny on earth kind of looks a lot like every other penny. And what if we were, and whenever they're being manufactured, we could honestly say that there's probably little variation from one penny to the next. Let's assume that they are perfectly equal. But in reality, those may be 2 distinct pennies. So we had to kind of take ourselves back from whenever we're considering abstract objects to objects that actually mean something as an instance. Okay? So even though we have 2 pennies that may be identical, they are 2 distinct instances of a 1 cent value. But when we back up and we think about numbers like 2, there is only one number 2. We don't really have 2 instances of the number 2. We only really have one number 2. It's like pi. There is no different instances of pi. There's only pi. But with humans, we have different instances. With pennies, we have different instances. So that's somewhere where we may have to be very clear about what we're defining equivalence to mean, right? And we're going to get into these deeper topics later, but for right now, let's not go into the woods too far. In general, we don't allow duplicates. We may have to sometimes define what a duplicate may be, even when it's maybe not clear, but that's for a little bit of a deeper mathematical conversation. We get into equivalences and things of this nature where we start kind of effectively doing what we do in C++ and object-oriented languages, where we overload functions, where a function may have the same name but different parameters, and so we treat it like a different function. We may be doing that. We may start overloading the notion of equivalence or what it means to be equal to some definition, but that's for a later date. So what are the two properties of a set? Sets do not contain an order, which means we could rearrange the elements any way we want to, and sets do not contain duplicates. That means if an element's already in there, adding another one just means that the set doesn't change. Now, let me show you some symbolic stuff about a set. Let's suppose that we have set T, and set T is going to have the colors blue, green, red, orange, and let's just stop there. Now what we're going to say is blue, from now on, we're not going to talk about kind of vague things. We're actually going to use a label. Blue is an element of set T. So what I would do is I could say blue is an element of set T. Now, this is kind of a sentence. Now, what do we say? Mathematics, set theory is the very basis of the mathematical language. It's kind of one of the fundamental parts of it. But if we're writing this out, blue is an element of set T, doesn't that seem like the only person to be able to understand that is someone that can speak English? And to some extent, you'd have to be kind of far along in your understanding of English to start piecing this together with words like an element of set T, whatever, right? That goes a little bit beyond just saying hello. Okay, so when we have this, you guys may guess that we need to be able to represent this symbolically, so that way the folks that speak Chinese, the folks that speak Japanese, the folks that speak French, the folks that speak Spanish, everybody will be able to see this without it being in like English form. The way we represent this symbolically is we do this. T is an element, sorry, I've screwed up. Blue is an element of set T. Now what you guys need to think of, this means element in the set. Blue is an element of the set T. All of this sentence, blue is an element of set T, gets condensed into this mathematical expression. Now, that is an entire sentence that basically gets condensed down into three symbols. Blue, that symbol that looks like kind of a rounded back E. It looks like a lowercase e, but it's not quite. I'm going to draw it a little bit bigger so where everybody can see it. The way this symbol looks is it looks like it's kind of a perfect circle back, kind of a half circle, and then you have this line right through it. That's what that looks like. An element of, right? That's what you say when an element is inside the set. There you go. Not too bad, right? Now, notice that not every color is here. Does everybody agree that yellow, I could write it out as a sentence, yellow is not an element of set T. Can we all agree on that? Yellow is not an element of set T. Okay. Now, everybody here knows that I've kind of don't like sentence form. We want to kind of reduce this down into an expression. It turns out that this is very easy. We say yellow is not, and we draw a slash, an element of T. Typically, when you have a mathematical symbol and you draw a slash from the upper right to the lower left through the symbol, it basically means you just append the word not in the sentence. So if you're speaking whatever language, you would see that slash, and then whatever language that you would say the word not in, that's what you would apply. And then this symbol, this expression, means yellow is not an element of set T. Yellow is not an element of set T. So at this point, you guys know how to represent an element that is in a set. You represent something that's not in an element of the set. So let's try some examples here. Let's suppose that we have set W, and then we say this is the set 0, 1, 2, 3, dot, dot, dot. Now this is a set that goes to infinity. It starts out at 0. Remember what sets don't have? Sets do not have an order, but I wrote these elements in order just to kind of make it easy so I could use this dot, dot, dot notation to show that there's a pattern that's being established. So, is this a true statement? Is 7 in W? Is that a true statement? We would say, yes, that is a true statement. Would we say this? 2/3 is not an element of W. Is that a true statement? We would say, yes, that is a true statement. We would then go over here, maybe try it again. We would say -4 is an element of W. And then what would we do? We would like scream and shout, and we'd say, no, that is not a true statement. That does not work. And so how can we make it a true statement? We would say -4 is not an element of W. And then at that point, we would say that is a true statement. Okay, so remember, we can use the not symbol by just making a slash through the symbol, and we've effectively got it. Not too bad, right? So set theory, a lot of fun. I hope you guys are starting to realize that this is a language and how we can condense very big sentences down into this. This is just the very first day of learning the mathematical language, or learning the language of mathematics, and you see that we've already condensed sentences down to just 3 symbols. Now there's one more thing we need to talk about, and then this lecture's over with. It's going to be cardinality. Cardinality. This is just our fancy way of saying the number of elements in a set. That is all it is. It's just simply the number of elements in a set. And, you know, if you think about the number of elements in a set, it really is just counting the elements. So let's do some examples. Let's suppose I take the set, let's suppose I'm going to define the set A. We can reuse this A. I know I've already defined it, but we'll just keep on with it. 2, 5, 8, -4, and 1. Now, remember what we said? Sets do not have an order, so it doesn't matter if these are written kind of in this funky way. It's okay. Now, the way I represent the cardinality is I do this. I put the absolute value symbol around A. And then I would say, how many elements are inside there? 1, 2, 3, 4, 5. The cardinality of set A is 5, which means what? Set A has 5 elements. This expression effectively represents this sentence. That's effectively it. Set A has 5 elements. That's all it is. Now, we do have to be a little bit careful about something. Let's go back to our set W that we defined earlier. This is 0, 1, 2, 3, dot, dot, dot. Now, what do you guys notice about this? This set goes on forever. It doesn't have like a finite number of elements. And that's a good thing to say, actually, because we say that set A is finite. We say that set W is, as the Lady Gaga song says, infinite, or what you may hear, infinite, right? So we have finite sets, we have infinite sets. Infinite sets means that this set goes on forever. There's no kind of like finality to it. Finite means that we could actually count the elements. Now, we do have a way of representing this. We have the absolute value around W, and sometimes what you'll see people do is you will put this infinity symbol. It's very common for this infinity symbol to represent something that's infinite, whatever. That's pretty common. Now, there's one thing that we need to keep in mind, and this is kind of just like maybe something being very technical. It's just kind of around for completeness purposes. We say the cardinality for finite sets have a cardinality. Infinite sets do not have a cardinality. Now, you may say, well, you said it's infinite. Infinite is not a value. You can't multiply infinity by 2. You can't divide something by infinity. You can't multiply by something infinity. If you guys remember back to your calculus class, infinity is a notion. But if you remember, if you don't mind me kind of going down your calculus class, whenever you had a limit that went to infinity, you said what? You would write D and E, which means does not exist. So finite sets have a cardinality. Infinite sets do not have a cardinality, or their cardinality does not exist. Now, with that said, we do sometimes use this notation. This notation is just symbolic. This is a symbolic representation. Infinity is not a value. It is not a real number. It is not a value that you could do anything with. It's just a notion. Infinity is a notion. So we have infinite sets do not have a cardinality. Finite sets do have a cardinality because their values, their cardinality is actually a value that's a number. Infinite sets, they do not have a cardinality because infinity is not a number that you could do anything with. All right, so this little thing that I just circled here, that's just for symbolic purposes. So anytime that you see the cardinality is equal to infinity, an infinite set just means that it just designates an infinite set. That means that the number of elements go on forever, that there's no finite bound to the number of elements that they have, and that it does not have a cardinality. We do have that symbolic representation where it looks like it has a cardinality, which we call infinity, but that's just for symbolic purposes only. All right. So if on a question that we have on a homework assignment and a set is infinite and we say, what is the cardinality? There may be some sort of instructions about what it means. Maybe you'll say D and E does not exist. Infinite sets do not have a cardinality. Finite sets have a cardinality. Okay? So with that said, we have sets, set cardinality has two options. One, we have finite sets, where the cardinality exists. Then we have what we refer to as infinite sets, where the cardinality does not exist, just like with limits from your calculus class. Now, if you didn't have calculus, that's perfectly fine. Hopefully someday you'll take one and then you'll have all this you can stand. It was D and E and does not exist and all these other things. But just keep in mind, cardinality, finite sets have a cardinality. Infinite sets, they do not have a cardinality, does not exist. How do we sometimes represent infinite sets? We put the absolute value bars and we do this. Now, I do want to make a point. Some of you guys feel like that's awkward to reuse absolute value. A lot of times in mathematics, whenever you see a symbol or a notation being reused, it sometimes means that there are some similarities between its usage, but that similarity may be kind of abstract. So if we think about what is the absolute value of a number, it means how far away it is from being 0, correct? 5 is 5 units away from being 0. -5 is 5 units away from being from 0. What does it mean, the cardinality? Why do we use that absolute value? Well, if it has 5 elements, that means that's how many elements away it is from being empty, a set that's being empty, right? Okay. Now, with that said, we want to discuss one more notation. Let's look at this. Let's suppose that we have the set F. This is just a letter that we name. We're going to define the set F, and I'm going to do this. And I'm just going to put an open brace, and I'm going to put a closing brace. Now, what this actually looks like is it's the set that's empty. This is referred to as the empty set. Now, I want everybody to pay attention that I put the word "the" there. In mathematics, any set that's identical and has the same elements inside of it, even if they're rearranged, we say the two sets are equal, even if they've been written with the elements in different order, because order doesn't matter. The empty set, the reason we say the empty set is because every set that has nothing in it is effectively equivalent to any other set that has nothing in it, And so we say there is only one empty set since they're all equivalent. And so from then on, we refer to it as the empty set. Now, with this notation is a bit dated. Just a bit. You'll see it around somewhat, but it's a bit dated. We sometimes now see this notation. It's become more popular, and especially maybe in the 1900s, it became a lot more popular when we had machines that could do typesetting fonts and have all sorts of new symbols that we could put in textbooks and stuff, to where we have this symbol. It's basically, if I can draw a little bit bigger, it's basically a perfect circle with a slash going through it, to where the slash kind of slightly goes beyond the perimeter of the circle by just a little bit on the upper right and the bottom left. This is the symbol for the empty set. That is the symbol. This is the modern symbol for the empty set. Now, a lot of you guys are probably wondering how cool I am. Well, it turns out that I'm a very well-versed person in culture, and I'm actually going to show you something that I think is pretty cool about this symbol. For those of you guys that are kind of into music, there was a band that had a couple of hits a few years ago, and this band was called 21 Pilots. If anybody's familiar, I think they had a song called Heathens or something like that. I don't actually remember the name of it. If you were to look at the cover album for that band, you would see that they had the empty set as 21 Pilots. 21 Pilots. Their symbol kind of looked like this if I could draw it. T, but then they had this empty set symbol, and that's what their band looked like. Now, you may say, well, okay, so they just use symbols. Well, it turns out that this symbol was made popular by kind of a math cult at one point that was referred to as Nicholas Bourbaki. It was a group of mathematicians. This group of mathematicians sometimes had as few as 20 people in it. It had as many as 40 mathematicians in it. There was a lot of very famous mathematicians that were part of it. And so this group sometimes would publish papers under the name Nicholas Bourbaki. And they kind of, this has been kind of a rolling group of mathematicians. I don't know if that group's still around, but as early as 2000s, this group was still around. It was started, I think, in the maybe very late 1800s, early 1900s. Nicholas Bourbaki is almost like, it's kind of like kind of these kind of hidden author names. These people would publish papers under the name Nicholas Bourbaki, but it was actually a group of 40 of them, and this group, one of them would drop out of the group or they'd pass away, and then somebody would get inducted into it. It's kind of like almost, I wouldn't say cultish, but I put you in mind of that. They actually formalized some of the symbols that we use in mathematics, and a lot of people credit this empty set symbol with the group Nicholas Bourbaki. Now, if you're more curious about more kind of strange occurrences in culture of music, one of the 21 Pilots song, I'll leave it to you guys to actually look it up. I don't remember the name of the song off the top of my head. But they actually make a reference to Nicholas Bourbaki. Google that while I'm doing this video if you don't mind. Google Nicholas Bourbaki in 21 Pilots song, and you'll hear this band actually make a reference, something on the lines, I refer to Nicholas Bourbaki. I can't remember how the lyrics go actually, but if you look it up, you'll see it. And it's just kind of weird that they, or kind of strange, maybe kind of fun, that they put the empty set in kind of their band kind of symbol or their album art, and then they make a reference to the mathematician cult group that formalized that symbol or made that symbol popular or created that symbol. So anyway, for those of you guys who are wondering how cultured I am, hopefully that made you realize just how cool I am by having this kind of knowledge about pop culture. Anyway, so that basically sums up the empty set. There's one thing that I want you guys to be aware of. There are two ways to represent the empty set. You could have that open and closing braces, which is essentially roster form with nothing in it. Or you can do this. All that I ask is that you don't do this, because this is completely incorrect. This is the set containing the empty set. Now, with that said, I want to describe what a set is. Does everybody remember how I described a set as being an abstract container of sorts, kind of a container to hold mathematical objects? Sure. What that means is anytime an engineer or a mathematician declares a set, What you should imagine is that you're reaching up into your cupboard and you're actually putting a bowl on the table. You're actually reaching up and putting an abstract bowl on the table. Now, in my cupboard right now, I have bowls that have nothing in it, but they are bowls nonetheless, right? So if you take a bowl from your shelf and put it on there, you still have a bowl even if it has nothing in it, correct? That doesn't mean the bowl doesn't exist because it has everything in it. It just means that it's a container with nothing in it. That's what the empty set is. The empty set is effectively a container that has nothing inside of it, but it is still a set. So this symbol right here, what does that mean? That is a set containing an empty bowl. So think about that. You actually can put a bowl inside of another bowl that's empty. Imagine I take an empty bowl and I put it inside of another bowl. That inner bowl has nothing in it. It has a cardinality 0, but it turns out the other bowl contains an empty bowl, which means its cardinality is 1. So let me define this for you and wrap your head around this and make sure you get it. Let's suppose that I'm going to say the set M is equal to this. This is effectively a set that contains the empty set. So what do you think the cardinality of M is? It's 1. It is a set that contains the empty set. So that outer set actually contains an element. It's just a set that's empty. So what does that mean? Sets can contain other sets. So take a look at this. I could define maybe set P to look like this. This is a set that contains a set 1, 2, 3, another set 4, 5, 6, 2, another set 1 and 3, and then another set, the empty set. So at this point, I would say that 2 is not in P, but I would say that the set 1, 3, the set containing 1 and 3 is an element of P. Make sure you understand the difference. Why? You may say, well, 2 is inside here. It is, but it's inside of a set. 2 is not in here by itself. 2 is just inside of a set that's in a set. So we say 2 is not an element of P, but we would say 1, 3, the set containing 1 and 3 is an element of P. Make sure we understand that. And we know that the empty set is an element of P. So these are all true statements. Now, this can get quite complicated, and so sometimes what we'll do is we'll give these individual sets a name and then place them inside of other sets to keep things simple. You may start realizing that this kind of has a kind of the look of computer science. We create individual arrays, and then we put arrays in the array. So if we think about this, how do we develop matrices in computer science? In computer science, a matrix is essentially an array of arrays. Now, an array is different because arrays have an order. You know, the first element has to be indexed as 0, the next one 1. In a set, they don't have an order. So think of those as like dictionaries. You can have dictionaries within dictionaries or hash maps inside of Python dictionaries, right? Or Java, whatever the case, or C++ for that matter. Unordered maps in C++, hash maps in Java, or dictionaries in Python. All these things could exist. All right? So hopefully you're seeing this connection between the language of mathematics and the language of computer science. Hopefully you're starting to draw some parallels and you're starting to see where these things happen. All right, so with that said, I appreciate your attention on this introduction to set theory. Hopefully that you understand this a little bit more. Hopefully you have kind of an understanding of the introduction of sets, how we represent sets, the 3 ways we can represent them, the pros and cons of each one of those, what it means to be an empty set, what it means to be a set inside of a set, what it means to represent a set using set builder form, being able to determine and symbolically represent whether an element is inside of a set or not, so on and so forth. So thank you for your attention. Hopefully this was helpful and interesting, and I will see you guys at the next lecture.